Thank you, Amit. Before I start talking about the program, let's talk about what's really happening inside the system that the program is controlling. In our system, we are using MOSFETs in a switching application in order to pulse current into each of the heating elements from the voltage regulator. The user can change temperature setting from the user interface using push buttons and viewing this on the LCD screen. The Arduino then adjusts the heating for the system by reading in data from the temperature sensor and adjusting the pulse width modulation signal. This pulse width modulation signal can be seen here, for example, in this graphic. The dotted black lines indicate the pulse width. Within the pulse width, we have the duty cycle. At a 25% duty cycle is on for 25% of the time and off 75% of the time. At a 50% duty cycle, on half the time, off half the time, and so on. By increasing the duty cycle, we are increasing the amount of time that is on, therefore increasing the average power delivered to each of the heating elements. This is how we can increase heating. Once the desired temperature setting has been met, we then decrease heating in a similar manner by decreasing the duty cycle. Through the Arduino's programming environment, we're able to accomplish several things in software. First, we're able to load the last saved temperature settings from the EEPROM, which is the Arduino's flash memory, a non-volatile memory for data storage, so that when the user powers off the system, for example, to exchange battery packs, the next time they power back on, the last temperature settings would have been saved and they will be loaded and they can begin heating it. We're also able to take input from the user via push buttons so that the user can initialize heating for the system as well as change temperatures for each glove and boot individually. We're able to have the Arduino generate the pulse width modulation signal to the gate of each MOSFET in order to pulse current and control heating for the system. We're able to read in data from temperature in each device via temperature sensors in order to adjust the heating algorithm for the system. We're able to read a voltage from the battery in order to determine the remaining battery level for the system. We were then able to display this battery level, the selected device, and its corresponding temperature setting onto the LCD screen. Here we have the software flowchart for our system. After powering on the system, we then display the welcome message. We then retrieve the last temperature settings from the EEPROM, initialize button pins as inputs, then set the frequency for the pulse width modulation pins. After successfully setting those, attach button interrupts and initialize temperature pins. Then, after a delay of 5 seconds to allow time for the user to see the welcome message, we then read the battery level and display the menu, which includes the battery level, the selected device, and its temperature setting. We then attach functions for temperature reading, battery reading, and heating to the internal timing function of the Arduino. We'll then continuously check for button presses and service events attached to the timer. Here we have additional flowcharts for the timer functions and button press functions. For timer functions, the Arduino will check the time and at every 1 second interval will read data in from the temperature sensors in each glove and boot in order to determine the temperature. Also, every 1 second, if heating has been toggled, it will check the difference between the set and red temperature in order to adjust the pulse width modulation signal set. Every 10 seconds, we then read the battery level and display this to the LCD screen. For the button press functions, if the standby button is pressed, it'll toggle heating for the system. If the select button is pressed, it'll cycle display of the selected device, left glove, left boot, right boot, and its corresponding temperature setting, off, low, medium, or high. If the up button is pressed, it'll increment temperature setting from off to low, low to medium, medium to high, or stay on high. If the down button is pressed, it'll decrement temperature setting from high to medium, medium to low, low to off, or stay off. I'll now welcome up Mike and Lou to walk you through hardware implementation and PCB design.
Thank you, Eno. The primary components of our integrated C-SU heating system consists of the widely used Arduino microprocessing system, switching MOSFETs, pictured here, used in conjunction with a voltage regulator to pulse control current to the heating elements of each device. Temperature sensors located in each device to measure heat levels, and connectors that are waterproof to ensure waterproof connection between. between the soup and each device to make sure that there is no short circuit. Our SKISU heating system is powered by an 11.1 volt lithium-ion battery rated at 4,400 milliamp hours. The battery, pictured here along with its charger, has an expected life of about 3 hours, which is about the same amount of time it takes to fully charge the battery. That is why the battery is easily detachable, allowing the user to carry multiple battery packs for extended battery life. The battery powers the Arduino, heaters in each device, as well as the MOSFETs and voltage regulators. The user interface for a SKISU heating system features a switch, buttons, and an LCD display for the user to interact with. The switch, pictured here, when pressed down, will power on the entire system. The standby button, when pressed, will turn on and off heating for the entire system. The select button, when pressed, will allow the user to switch between each device for which they will set the temperature. The up and down buttons allows the user to increment or decrement the temperature setting for each device. The LCD will flash for a device that has a temperature setting of on, low, medium, or high, and will continue to flash until the desired temperature is met. Our printed circuit board was created using the Express PCB computer-aided design tool. It is a two-layer board with components mounted on top, as shown here. It is then attached to the Arduino microprocessor, which is affixed to a water-resistant box. Our PCB contains test points to check for quality and ensure there are no bad connections. Our circuit also features the ability to implement a battery monitoring integrated circuit to measure the battery levels. However, that was not implemented in this phase of the project due to time constraints. Instead, we performed a voltage divider across the battery to estimate remaining battery life. I will now present to you Kevin Eccles, who will summarize and conclude our presentation.
Thank you, Michael. After completing our suit, we first decided to do some post-integration testing. This first test, was the cold start test. The glove was chilled to 32 degrees Fahrenheit, and then a sock was put inside the glove to prevent heat loss. It was plugged into the integrated SKISU heating system, and using our heating algorithm, we heated the glove for 30 minutes. And let me stress again, this was in outdoor climates of 45 to 50 degrees Fahrenheit, so we took the glove from the freezer and moved it to outdoor conditions for testing because we couldn't test inside a freezer that was large enough. These results are without a hand in the glove, so there's no body temperature that's helping to increase this. This is purely hardware. So as you can see here, at time 0, we begin at about freezing, and we gradually make our way up to about 63 or 64 degrees Fahrenheit in 30 minutes, which is adequate. It's not too bad, but as you can see here, there's a great spike of heat until this point in about 13 minutes, where the soup gradually declines. We believe this is partly due to the 5-volt regulator that we put in place as a precautionary feature to assure that we would not burn out any more heating elements, as I'll explain shortly. After the 30-minute cold start test, we decided to put a hand and foot inside the glove and boot. Again, the gloves and boots were chilled to 32 degrees Fahrenheit. A hand was put inside, and it was plugged into our suit using our heating algorithm for 7 minutes. It was tested in outdoor climates, again, 45 to 50 degrees Fahrenheit. And as you can see here, the glove is great. However, the boot, a little room for improvement there. So they both start about 81 degrees Fahrenheit. The glove makes its way, the boot makes its way up to about 88 or 89 degrees Fahrenheit before we cut off the test. The glove, on the other hand, makes its way up to the 100-degree mark, which is exactly what we wanted to see within about 2 to 3 minutes, and then it begins to modulate itself. So as you can see, we overshoot that 100-degree mark, get up to maybe 103, 104, and then gradually begin to decline as we come close to that 7-minute mark. This is exactly what we were designing to do, and it's great to see these results in a graph. In summary, what we've really developed here is a working prototype that with future work could potentially be a sellable idea. It's a completely mobile system, meaning that the battery drives the entire system by means of switching MOSFETs and a 5-volt regulator. The microcontroller is capable of communicating with various components in our system, such as the switching MOSFETs, which are used to control the heating, The temperature feedback system, which features temperature sensors used to read data back into the Arduino microcontroller to adjust the heating algorithm accordingly. And the user interface via push buttons and LCD screen, which allows the user to turn the heating on and off, as well as control the heating of each glove or boot independently from the others. The user interface also allows for the user to monitor the system in terms of a battery life remaining, as well as a heat setting, and the user will know how long it takes for the suit to heat up because of the flashing heating level indicator. Some future improvements we could see being made to the integrated ski suit heating system. If this project was to be picked up by another team in the future for a phase 2, we'd like to see them incorporate the heated jacket and pants for the suit. We think that would be a great design challenge, as well as create a smarter controller that can sense abnormal conditions, such as a break in the ski suit conduit, which could prevent the suit from heating. We would like to see the next team kick off the 5-volt regulator training wheels and go ahead and switch the full battery power across the heating elements. We would like to see the next team also incorporate a more sophisticated battery monitoring system by means of the battery monitoring IC that Michael was talking about earlier. The next team could also use our phase 1 testing to better define their hardware specifications. We were using proprietary information from Hottronics that gave us a temperature range of about 60 to 160 degrees Fahrenheit. Once we implemented the suit, we were unable to achieve this temperature range. And as a result, our hardware is a little bit, it's larger than it needs to be. We believe that the next team could improve our packaging of the control unit by making it more water resistant, lightweight, as well as more comfortable. It's kind of a little bulky at this point in time. And we also believe that the next team could incorporate a better user interface location, such as through a smartphone application or on the wrist of the glove, so that the user can change the settings as he rides the chair to the top of the hill. Some reflections on this project. Unlike our other engineering class, this class has been very hands-on. We were able to solder components to a PCB that we ourselves created based on a circuit schematic that we ourselves engineered. As a team, we learned how to divide, delegate, and prioritize tasks according to each member's strengths and preferences, which meant that each team member, when they came into work on the project, really enjoyed what they were doing. Some advice to other capstone groups would be to be wary of using proprietary hardware without schematics. As I mentioned earlier, we had burnt out a couple boot heating elements because we didn't understand the inner workings of them. We knew we could make them heat by applying a voltage. However, when we put them in the switching application, they burnt out, setting us back about a week's worth of work. Another point, make sure you have a proper understanding of how lab equipment makes its measurements, and as well as what settings you need them to be on. An example, we were using a digital multimeter and current sensing at the drain of our MOSFET, and for some reason, it took us actually a few days to troubleshoot as to why we couldn't get that MOSFET to switch for the life of us. It wasn't until we talked to Wayne, he suggested that it could be the digital multimeter there. We would suggest doing design reviews of both your hardware and software systems with your team internally, as well as with your advisors. This will help prevent circuitry that may not function in the second phase of capstone. Don't underestimate the complexity of your components. If the component has a 30-page data sheet, there's likely a reason for that, and it's probably going to take longer to incorporate as a result. Do not be afraid to seek advice early in the first phase of your capstone project. We have a great professional society here at the University of Washington, Bothell that can help you with your circuit design, likely building it better than you yourself could. And one thing that I'll stress the most is do not hesitate to get started on your breadboard testing or circuit simulation in the first phase of capstone. If we were able to completely characterize the heating elements of our suit, we would have been able to better define our hardware specifications and as a result build a better working prototype. We'd like to give special thanks to Dr. Arnold Berger and his ski shop for being our industrial mentor in this. Dr. Wayne Camaro for being our academic advisor. We appreciate you, Wayne, and all that you've done for us, helping us get there. We would like to thank the University of Washington, Bothell for their sponsorship of this project. Because Arnie was our industrial advisor, the university actually backed us financially for this project. We would like to thank Chris with the University Bookstore for allowing us to use her mannequin, which you can return tomorrow still. And we would like to thank Tracy Gibbons, who is the owner of Sturtevant Ski Shop. And she actually donated the suit to us, both the suit and pants. And without which, honestly, our budget would have been a lot tighter. We'd like to thank all lab technicians, including Cole Burbach, for his generous help and work on our project when he had his own stuff he needed to be doing. And we'd like to thank our colleagues Kelly Welsh, Trevin Jorgensen, and Joshua Jai for their help in troubleshooting our circuit design. That concludes the integrated ski suit heating system presentation. Thank you.
Because Questions? Questions?
Guys are making it too easy.
So you got it up to like 100 degrees inside the hand. That seems like really hot if you're actively skiing as well, right?
Yeah.
You should probably like keep it down to maybe 70.
Well, if you were at Breckenridge and it was 5 below, probably would not be that hot and below.
Not to mention too, this is a universal ski suit, so it could be incorporated in a snowshoeing situation or, snowboarding. It doesn't necessarily have to be skiing. It could be a multitude.
And we do have different levels, low, medium, and high for your instructor.
You said you use pulse width modulation to control the heating.
Yes.
And was that software controlled, or did you have some digital logic to do that?
Yeah, that was through the software.
All software?
Has a pulse width modulation, certain things I can just send out pulse width modulation. And we just adjust the Dewey cycle, like I said before, in order to apply a certain amount of heating at certain levels.
Have the team given any thoughts of how to increase the autonomy of your system for longer than 3 hours?
Yeah, that's a good question. So the question was, he asked if we thought of any ways that we could make this suit last longer than 3 hours. To answer your question, honestly, no, we haven't. However, earlier my brother had mentioned something about using a solar panel on the suit as well. Charge the battery. It could potentially work.
The battery we currently use isn't extremely heavy, so you could carry potentially multiple battery packs, and then as soon as your one battery pack runs out, you can just switch it out because it's easy to unplug.
Other questions? If not, let's thank you. Okay, I'd like to take about 5 minutes, get up, stretch your legs, and let the second team